Here you can see that each of the group members are transferring enough solution into the cuvette, but not too much.
Here she is wiping two sides of the cuvette.
Here we're zeroing the spectrophotometer. Failing to zero the machine with a blank would result in the absorbance being less accurate. Here we're making sure the spectrophotometer door is shut for scanning.
Here you can see that Nisa is putting the cuvette into the spectrophotometer with the correct sides facing the beam. First, we scanned across all wavelengths. We did this for two reasons. The first reason was to find the lambda max. The second reason is to ensure a high sensitivity when scanning our samples at a specific wavelength. The lambda max is defined as the wavelength at which a substance has its strongest photon absorption.
Here Nisi is removing the cuvette and closing the door.
Here Palak is scanning the absorbance of the sample.
Here you can see that Palak is recording the absorbance of the sample in the notebook.
The relationship between concentration and absorbance is directly proportional.
Here I am cleaning the beakers and all of the other tools thoroughly and wiping them down with a paper towel afterwards. The Beer-Lambert law is A equals epsilon times C times L. A is the absorbance, epsilon is the molar absorbent coefficient, C is the molar molarity, and L is the path length.
The absorbance is measured by a spectrophotometer, and it is based on how much light is absorbed by the sample. The molar absorption coefficient can be found by calculating the slope of a absorbance versus concentration graph. C, which stands for concentration, can be found by measuring the molarity of the solution. The path length is determined by the distance that the light travels. Here you can see that all of the data is recorded with the labeled samples of D1, D2, and D3. You can also see that the absorbance data is recorded for all of the samples and that the significant figures for the volume are recorded to 2 decimal places.